Welcome to the first of two lessons in equilibrium calculations. In this lesson, we're going to learn type 1 of two types of equilibrium calculations. In these calculations, we will either be trying to find the equilibrium constant, so in this case we'll be given information of the equilibrium concentrations of a particular system, and we'll use that information in order to calculate the equilibrium concentration. This is the same kind of calculation we'll do to study the lab that we did of the iron and thiocyanate solution, where we use the colorimeter. The point of measuring the absorbance is to help us to measure the concentration of the iron thiocyanate ion at equilibrium, and then we'll use that information to calculate the equilibrium constant. The second type of calculation is one where we're given the equilibrium constant, and we'll use that information in order to help us to calculate the equilibrium concentrations of the system. In order to organize our information in these types of problems, we use what's called an ICE diagram or an ICE chart. In these charts, the I stands for initial, the C stands for change, and the E stands for equilibrium. These 4 points summarize some important facts about solving these types of problems, and we'll come back to them after we've looked at an example. In this example, it's type 1 determining K. So we're going to use the information in this problem to help us find the equilibrium constant for this reaction. The question states, suppose that there are 2 moles of HI in a 1 liter flask at 425 degrees Celsius that react to produce H2 and I2. When equilibrium is reached, the concentrations of H2 and I2 are determined to be 0.214 mole per liter. Calculate the Kc for this reaction. Now we always need to start with a reaction, and in assignments and tests you'll be given the reaction, but in problems we'll often develop them. So let's start by writing the reaction. We are told here that we are putting HI in a flask. So we've got HI, and it's going to be in equilibrium with I2 and H2. So those are the products as stated in the question. Now when you set this up, these become the columns of your ICE chart. And on the left-hand side, we'll write ICE so that we can report our initial, change, and equilibrium concentrations. Now this equation is not balanced, so we need to put a 2 here. So what we've got developed here is a chart where the columns come from the reactants and products, and the rows come from the I, C, and E. Now what we're told is that initially we put 2 moles of HI into the flask. And these are concentration tables, so we always need to work in concentrations. And this is because in the end, ultimately, when we solve for our equilibrium constant, as you know, the equilibrium law is in terms of concentration. So when we're told that 2 moles of HI is put in a 1 liter of flask, that means that we've got our N is equal to 2 and our V is equal to 1. So we're starting initially with 2 mole per liter of HI. And the strategy that I use so that I can be sure I'm following significant digits is when I enter numbers into my ICE charts, I put them with the correct number of significant digits. Now in the problem it doesn't give us an amount for H2 and I2. And so initially they're going to have a concentration of 0. And that's a really important fact. Initial concentrations in these diagrams are the concentrations of the substances before any reaction has occurred. So although as soon as we put the HI in the flask, the equilibrium would start happening and there would be I2 and H2, when we talk about initial, it's before any of that has happened. So if there's no mention of a quantity of something, then we know that it's going to start at 0. The next row that we'll fill in is the change row, and the change row is always in terms of x. So we know that these are going to change, the concentrations, as we approach equilibrium, but we don't know by how much. So we're going to put the amount that they change by in terms of x. Because the concentrations of the I2 and H2 have started at 0, we know that they, as they approach equilibrium, are going to have to increase by some amount. Now, one important fact here is that the reactants and products will always have opposite signs in terms of the change. And think about it like a teeter-totter. If the products go up in concentration, that must mean that the reactants have to go down. We need to use some of the reactants in order to make some product. Now, when we put them in terms of x, we need to reflect the stoichiometry of the actual reaction. So, as we make some amount, we'll say x of I2, for every 1 mole of I2 that I produce, I will also produce 1 mole of H2, as seen from the coefficients in the balanced equation. At the same time, for HI, there's a coefficient of 2. And that's showing us that for every 1 mole of I2 that's produced, I needed to use 2 moles of HI. So in this case, it's going to go down by 2x. So our changes in our ice chart are always going to be in terms of x. The signs of them being positive and negative are always going to be opposites for all the reactants and all the products. And the amount by which they change is going to reflect the stoichiometry of the balanced chemical equation. Now for our equilibrium row, we want to know what the resulting concentration is. We started with, for HI, a concentration of 2.0, and we've decreased by some amount 2x. So at equilibrium, the concentration is going to be 2 minus 2x. And I don't know what x is at this point. The I2 started at 0 and it increased by x. So at equilibrium, it's going to have a concentration of x, which will be the same for the H2. Now, in type 1, determining the equilibrium constant, what you'll always be given is information about one of the substances at equilibrium. So if we look back to the question, it says, when equilibrium is reached, the concentrations of H2 and I2 are determined to be 0.214. The word determined is just telling us that it's been done by experiment, because as you know, equilibrium constants must be determined from an experiment. So this isn't a calculated value, this is an experimental value. So what we know is that the concentrations of I2 and H2 at equilibrium, they're equal to x, but they're also equal to 0.214. So what this information has given us is the concentration that x is, because x is equal to 0.214. So anytime you're given the concentration of something at equilibrium, what that's going to help you find in your ice chart is the x value. Now that I know the x value is 0.214, I can plug back in here so that I can also find the concentration of the HI at equilibrium. Okay, so I plug that information in, and the value that I get is 1.572. You may want to pause the video at this stage and make sure that you understand how that calculation was done, and you can practice it on your calculator. Now, because we were given information to find x, and we were able to find all the equilibrium concentrations of these substances in the system, we can now find the equilibrium constant. Because we know the equilibrium law, which gives us the relationship of the concentrations of the substances in the system at equilibrium. For this reaction, the equilibrium law is the concentration of I2 times the concentration of H2 over the concentration of HI squared. Now it's really important that when you're using this expression, because I'm calling it K, the only concentrations that I will plug into it are the ones from the equilibrium row. So it expects that these are equilibrium concentrations. So I can plug in the values that I have. And it's really important when you're plugging the values in to make sure that you keep the exponents that you've written from the equilibrium law. So you need to make sure that you remember to square the concentration of HI in this case. Now if I look back to my ice chart, I can see that there are 2 significant digits given to me in this value and 3 significant digits given to me in this value. So my final answer is going to be reported to 2 significant digits, which is the limiting one. Okay, so you should pause the video and plug this into your calculator and make sure that you are able to get the value 0.019, which has 2 significant digits. Of note as well is the fact that I didn't round until the very, very last step. I kept all the digits until this very last step. As you know, equilibrium constants do not have any units, so my final answer is that the equilibrium constant is equal to 0.019. Okay, so let's go back to the previous page to the summary so that we can see what important points are there for us to remember. So remember that the only values put into the equilibrium law are equilibrium concentrations. So from the bottom row of the ice diagram. All values in an ice chart are in moles per liter. The changes are in the same ratio as shown by the coefficients. So minus 2x plus 2x plus 3x, based on whatever the coefficient is in the balanced equation. And the change row should have signs to show the gain and the loss, and the reactants and the products are going to be opposite to one another. And if you look back to your chart, you can see all of those important points put into effect. At this stage, you can complete practice exercises 10, 11, and 12. Practice exercises 10 and 11 do not require you to set up ice charts. They're just helping you to review some of the concepts surrounding these types of problems. And number 12 is one where you can answer by setting up an ice chart.